Hey, so let's do number 29. And let me open up live view in a second. But the question is that we have a gamma ray, so high energy photons with 102 mega electron volts, which is actually enough to form that pair. But we're not forming a particle pair here. Instead, we are colliding with an electron, okay, and we'll scatter, and then if it's symmetric, then that means that both angles are equivalent, and so we have scattering angle theta and the energy of the scattered photons. So if we just wanted to kind of diagram what's going on out, we have, okay, so this is number 29, we have incoming gamma radiation in, right? So this is high energy, that's why I drew the high frequency. And then we have an electron being hit, so we have an electron here. And when you hit that electron scatters away, and a resulting new energy wavelength, new photon, emerges as well. Okay, so this is our electron. And if we went ahead and drew an axis that related, just the x-plane, then we would get some angle theta and an angle phi. And this is good to call this, okay, so in my problem I called it theta, so I'll call it theta. In the class we called it phi. And I know it's a little bit blurry, but it's the best I got. Okay, so from here, we're going to fill in a few more things that we know. We know that theta and phi are equal, so I'll just kind of set this equal to theta. And I know that we came in at 1.02 mega electron volts, okay? And then I'm going to fill in for what we're actually solving for. We're solving for the energy final, right? So EF, I believe, right? So the energy of the scattered photon right in here. I don't know why it's grayed out. And we also want to know the scattered angle of the photon. And I mean, either way, we can either solve for theta or we can solve for phi. They're going to be the same exact angle. So let's just say here, what is that? And, just for the sake of keeping everything organized, we're going to call it gamma, E gamma prime. This is going to be called E gamma. And the reason why I'm saying gamma is because it was gamma radiation, and it's just easier instead of writing P gamma because P's get redundant. And then this is going to be, we have, let's just say this is E electron prime. All right. And we have a few good things here. Okay. We have a few good things. We know that these angles are equal. So I'm already in my head thinking this is somehow going to relate to momentum. We know that we have some kind of initial energy, and we have initial momentum with that, so pi. But the initial momentum of the electron is 0, so I already know that as well. And we're going to combine all this. I'm just kind of brainstorming right now. And so if I imagine my pi component only comes from my photon, but my pf component, my final momentum, does include my electron and my photon. So somehow we go from having only one momentum to having two momentums, but those two momentums are linked because they have the same exact angle. So let's jump in to actually kind of solving this problem. All right. So first, we want to know E final. And I'm going to see, well, maybe Compton scattering's formula will tell me enough information I need to proceed. So we know that delta lambda, so lambda final minus lambda initial, is equal to Planck's constant over the mass of the electron times c, multiplied by 1 minus cosine theta. And what is cosine theta? Cosine theta is cosine of the angle made between the scattering. So, it would be better if I called this angle theta at the end of the day. Okay, so phi, we're now phi electron. Okay, so it's theta. All right, and now we say, well, do we have enough information to move forward? And the answer is, I'm just going to kind of check mark in green what we have. We don't have theta, so it's not check marked, but that's an X. We do have initial wavelength. We do have Planck's constant. We do have mass of the electron. We do have c. We are missing the final, and we're missing theta. And guess what? Those are the two things that the problem is asking. All right? And you might be asking, well, how do we know lambda I? Well, we know energy initial, which we can relate to lambda I using this formula. The formula is E is equal to h times frequency, where frequency is equal to, or let's say frequency times wavelength is equal to c. And so therefore, frequency can be written as c over lambda, which we can rewrite as E is equal to h times c over lambda. So now we have an equation for energy. All right. Well, what can we do with that now? We can solve for lambda initial if this is energy initial. So E over Planck's constant times c is equal to 1 over lambda I, and therefore hc over ei is equal to lambda I. So, okay, I have now successfully proven that we know this number. It is 1.02 mega electron volts, and we know these are constants. So I have proved to you that we do know lambda initial. And so now we're still stuck because we don't know lambda final and we don't know cosine. If we knew one of the two variables, we'd be golden and this problem would be very easy. But unfortunately we don't, so we have to keep moving forward. We're going to plug this value in a little bit later because we can just kind of solve for this as a, as its own little constant, right? Because it's just going to be a value. But the next thing we have to do is use our momentum conservation equations, because those will give us the most information. Because if you remember, if we have two particles moving at the same exact direction, one has mass with v and mass with negative v, the momentum will be mv plus m times negative v is equal to 0. So the final momentum of this particle-particle system will be 0. And why that's important is because we can cancel some things out, right? So this v and negative v we can say is equal to 0, is equal to pf. And so we're going to use that exact same logic in this problem to set up this problem. All right, so from here, let's go ahead and set up our first conservation, our most basic conservation formula. Pi is equal to pf. Always start here. And what is pi? Well, pi is the initial momentum of the system, and pf is the final momentum of the system, obviously. But let's just kind of talk about them as, like total values. And what we can do is we can define what is pi. So initial momentum, we have to do a little bit of a balance sheet. We can say what is the momentum of the photon and momentum of the electron, because it's going to be the sum of these, right? It's going to be the sum of these. And the initial momentum of the photon is given by E is equal to PC, because that's how we find the momentum of a photon. And guess what? We're given E, so that's perfect. And the initial momentum of the electron is mv gamma. Well, the velocity of our electron was 0, so this is actually 0. And so pi gamma is actually given by E over C. So perfect. So I will define initial momentum as the initial momentum gamma, which is equal to E over C. All right. And now let's define the final momentum the same way we did the other one. Final momentum. So gamma once again has momentum and electron has a momentum. Now don't be fooled to say, well, electron has no momentum because it didn't have before. Well, now the electron's moving, so it does have some kind of momentum, mv gamma, perhaps. But we don't even have to define it. We can just kind of define it as p prime electron. And our gamma piece will be p prime gamma. And the reason why I am not going to reduce this into that is because we can do some clever cancellations in this form and avoid this gamma term completely. because this gamma term introduces some funky things, and we really don't need it. We can deal with this problem in terms of energy instead of having to deal with this problem in terms of velocity. All right. So let's keep moving forward. Right now, the expression we got was that pi is equal to pf, and so for now we can just say pi gamma, because we know that. Like, we can keep that as that thing because it solves for something, is equal to p prime gamma plus p prime electron. So we have a kind of semi-useful form of this equation. And, you know, we don't really know what to do with it, because we have this value, but we don't have this value and we don't have this value. So it's kind of useless. But we can now do a little bit more magic, because we know some relationships with theta and we know some relationships with y. So we can break up pi gamma into initial x and y components, because pi is equal to pf, pix is equal to pfx. So if you have momentum in the, you know, piy is equal to pfy. If we have momentum, this can be broken down into the x components, and they should all still equal each other. So from here, we can define those. We can say that pix is equal to the only x component of our momentum initially is the gamma component at its full capacity, right? So we can say that that is just equal to pi gamma, or just p gamma, right? We don't have to specify pi because we have p prime. And that is equal to p final x. And p final x are the cosine components of these two primes. So p prime gamma cosine theta plus p prime gamma cosine phi. Sorry, not gamma, electron. All right, so we have one valuable form right here. Now let's do this in the y direction. Pi gamma, pi gamma, the initial one is equal to p gamma, and p gamma in the y direction, so p y gamma in the y direction, there was no y component to this guy, right? This doesn't go, like, perhaps if we had a problem that was something like that, well, then now we do have some kind of angle theta, but we don't have that, so we don't have to worry about that. So we can say the initial velocity, or the initial momentum component of the y direction, was 0. Now, again, the initial momentum component of the final is not 0. It is p prime gamma sine theta plus p prime electron sine phi, because this now has a y component to it, right? P electron it's a vector that has a x and y component to it. All right. So now we have two great equations. And we're going to turn this into an even better equation, because I know that what's the relationship between phi and theta? Well, phi is equal to negative theta, right? Because, you know, if this is angle 60 degrees, this angle is actually negative 60 degrees, right? Because this angle is actually 300 degrees or negative 60 degrees, all right? And so I can rewrite this as 0 is equal to t prime gamma sine theta plus p prime electron times sine of negative theta. The sine of negative theta, if we remember our unit circle, of negative, so if this is theta, and that sine component, let's just say, is a positive 3, that's going to be the exact same sign. This is going to be negative 3, right? This is positive 3, that's going to be negative 3. So sine of negative theta is equal to negative sine of theta. We can just say sine of theta the negative sine of theta is equal to the sine of negative theta, right? That's a trigonometric identity. So 0 is equal to p prime gamma sine theta plus p prime that or let's do minus, we'll put that minus out, sine of theta. And so now we have a valuable relationship between p prime sine theta is equal to p prime electron sine theta. And what we're saying is basically the y components of the electron and photon momentum are equivalent. Because guess what? Since these are equal, we can cancel them out. Right? So ultimately, we are boiled down to p prime gamma is equal to p prime electron. Wow, that is a very powerful statement, because the y components are equal, and since the angles are also equal, that means that the components are equal, period. Okay? So this is a critical step right here. And from here, we can now plug this in to our cosine equation to get something, something else that might be a little bit clever as well. All right, so I'm going to go to my cosine equation, and I'll play with it a little bit. So I'll go to my cosine equation. I'm just looking at my notes. That's why I got a little distracted. So my cosine equation, I can do some kind of manipulation here as well. So first, I'm going to manipulate with my angle variables. And I told you that the cosine, so the negative sine was equal to the negative sine of negative theta is equal to negative sine of theta. Well, what is the cosine of negative theta? Well, depending on which quadrant you're in, that can just be equal to the cosine of theta. Because look here. This x component in this triangle, like so, if this is theta and this is negative theta, the x component of the triangles are going to be literally equivalent, right? If this is 3 and this is 3, and this is like, let's just say this is 1, 3, and this is, 3, 1, this is 3, negative 1, the cosine components are going to be equivalent. And so what that means, and we can either use the trig identity or just kind of look at it, what that means is that cosine phi is equal to cosine theta. And now what that means is we can rewrite this as p gamma is equal to p prime gamma cos theta plus p prime electron cos theta. And lo and behold, what did we say p prime gamma was equal to? Well, it is literally equal to p prime electron. So from here, we can get rid of p prime electron because we don't really know what that is and we don't care. Well, p gamma is equal to p prime gamma cos theta plus p prime gamma cos theta. So now we have another equation. P gamma is equal to 2p prime gamma cos theta. So I will highlight another relationship we found. These are the important relationships we just found in this equation. So I'll just rewrite this here. P gamma is equal to 2p prime gamma cos theta. All right. So now we don't really know kind of what we can do with this. But let's just kind of stick in the energy relationships and see if we can find a lambda relationship and set that equal to cos theta. So, because if you remember, our Compton scattering formula is lambda final minus lambda initial is equal to h over mec times 1 minus cos theta. So if we find cosine theta, we can plug in cos theta here, get rid of cos theta, and then have our problem in terms of p's, lambdas, and things like that. Well, guess what? If we know our initial, our HMC theta, and then we get this in terms of a PI and PF, the only unknown left is PF and HF. And HF is directly linked to PF, so ultimately all we'll have left is HF. So I'll show you how we can do that in a second. That's just kind of some thinking. So P gamma is equal to the energy initial all divided by C, right? Because PC is equal to E, so P is equal to EI over C. So EI over C is equal to, all right, and I'm going to set that equal to 2P prime gamma cos theta. Well, I'm going to rewrite P prime gamma as P prime gamma is equal to E prime over cos, or EF, right? So EI over C is equal to 2 times the value of P prime is E prime over C, and I said E final over C, times cos theta. I'm going to solve for cos theta by canceling the C's first. I'm going to be left with EI over EF over 2EF is equal to cos theta. All right, so far so good. Now, another relationship between EIs and EFs, because we don't have our problem, right? Because if I'm trying to convince you that I'm going to get this all in terms of EF, this is not all in terms of, or lambda F. This is not in terms of that. So I have to do one more step, and I have to convert E is equal to HF, or E is equal to HC over lambda, where lambda, we can isolate that lambda term. So EI is equal to HC over lambda I, and EF is equal to HC over lambda F. So I'm going to replace everything. So I'm going to replace EI with HC over lambda I, all divided by 2 times HC over lambda F is equal to cos theta. So now you might be seeing what's about to happen. Everything cancels here, 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 and here. And so we're left with 1 over lambda I over 2 times 1 over lambda F. Now, these 1 over reciprocals end up inverting, and so we get lambda F over 2 lambda I is equal to cos theta. And now we have a very good relationship between what is cos theta in terms of lambda final, lambda initial, and we can plug that into the Compton scattering formula. So if I know that lambda final minus lambda initial is equal to H over MEC times 1 minus, and I'm going to plug that in now, lambda F over 2 lambda I can now solve for lambda prime or lambda F. So let's do that together. It's going to be a little bit of a doozy, but nothing too crazy. Okay, so the first step will be probably distributing this inside. So lambda F minus lambda I is equal to H over MEC minus H over MEC times lambda F over 2 lambda I. All right, and now let's add this onto that side, distribute out this guy, and then divide everything. So, okay, lambda F minus lambda I plus H over MEC times lambda F over 2 lambda I is equal to H over MEC. Now, I'm going to bring this to the other side. So lambda F is plus H over MEC times lambda F over 2 lambda I is equal to H over MEC plus lambda I. All right, and we know lambda I. We know H over MEC. Now we can isolate that HF. So HF is equal to lambda F, 1 plus H over MEC, okay, times 1 over 2 lambda I is equal to H over MEC plus lambda I. All right, and now all we have to do is divide. And now we get this complex monster, H over MEC plus lambda I, all divided by 1 plus H over MEC times 1 over 2 lambda I. We have successfully solved for the final wavelength. So from here, we are going to plug that in to get a final wavelength, because it doesn't ask for the wavelength, it asks for energy and the scattering angle. And first we'll do the scattering angle. So let's plug this in terms of what we have. Let's see. And I'm going to need to solve for lambda I first, right? So lambda I is equal to, we solved it up here. Remember, I kind of started with this. HC over lambda I. So HC over EI is equal to lambda I. HC over EI is equal to lambda I. And that is equal to, 6.626 times 10 to the negative 34 times 3 times 10 to the 8th, all divided by, our energy initial was 1.02 mega electron volts. So we have to multiply that by 1 times 10 to the 6 to get it to electron volts. And to get it to joules, we have to multiply by 1.6 times 10 to the negative 19. And that will give us lambda I. So let's do that real quick. Negative 34 times 3 times 10 to the 8th. 1.02 times 1 times 10 to the 6th. 1.6 times 10 to the negative 19. All right, so this gave me a value for lambda I to be 1.22, and I'll do 1.22 times 10 to the negative 12. This was the initial wavelength of that gamma radiation that was about to collide with the electron. Now, I'm going to also solve for this constant, just so we can have an easier time plugging it in. And that is given by 6.626 times 10 to the negative 34 multiplied, or no, just divided by 9.11 times 10 to the negative 31 times speed of light again, 3 times 10 to the 8th. And I'm sure we could have done some canceling here and there, but oh well. So this gives me 2.42 times 10 to the negative 12. And so now all we have to do is grind through this algebra. So I'll solve for the numerator first, or I guess it's not even algebra, it's arithmetic. This, okay, 1.22 times 10 to the negative 12 times answer. So the numerator is equal to that. And the denominator is equal to 1 plus that constant 2.42 times 10 to the negative 12 times 1 over 2 times our initial wavelength, which we determined to be 1.22 times 10 to the negative 12. That gives us basically 2. And so if we divide the 2.9578 times 10 to the negative 24 divided by 2, I think we did something wrong. 1 over 1.22, that, let's multiply it out, 1 plus, oh, so this was not a multiplication sign, this is a plus sign, right? We're adding this h over MEC term plus that, so this term is not 2.99, it's 3.644 times 10 to the negative 12, and so we get a lambda final of 1.8295 times 10 to the negative 12 meters. And immediately we have to ask ourselves, does this make sense? Yes, it does make sense. We have a higher final wavelength than original wavelength because we're a lower energy state now. And so now we can double check if we got our answer right by plugging it in to our cosine. How do we get cosine? We get cosine through this, hf over 2 lambda I. So hf lambda f over 2 lambda I is equal to cos theta. So cosine negative 1 of lambda f over 2 lambda I will give us theta. So I'll go to my functions here, cos negative 1 of, and since these are both 10 to the negative 12, I don't have to write the exponent. So I'll go 1.8295 divided by 2 times, I believe that was 1.218. And we get 41.32. I remember the answer in the back of the book does give you something like 1.22. Like, so the answer in the back of the book gives you is it 44.1 or something like that? I mean, we can check. The answer in the back of the book gives you for 29, sorry. 41.5. It basically comes down to how you rounded this value. So 1.82, 95, it literally comes down to how you rounded these values. So this is good enough, right? So we wanted 44.5, so, or sorry, this is 41.5, which is actually a little bit farther off. So let me see what went wrong here. It's not 1.28, it's 1.22. Sorry. There we go. So now, so it's still, I mean, it's still like within that. So 1.22 came from here instead of 1.28, and then 1.829 gives me 41.4 in great agreement with that answer. 41.44. Okay. Or yeah, we'd say 41.5. So from here, we can also get energy final, right? Because we related energy final to this very simple thing. So if we say energy initial was, our 1.02 megavolts, all right? And this just saves steps. For 2EF is equal to cos theta. So then 1.02 mega electron volts over 2 times cos theta will give us EF. Because now we don't have to convert anything between, we don't have to go from lambda to frequency to energy to electron volts to mega electron volts. We just save that entire conversion, because now we're going to go straight to here. So I will do 1.02 divided by 2 times cosine of 41.5, and we get an answer of theta is equal, or sorry, EF is equal to 0.6809 mega electron volts. Is that in agreement with the back of the book? 0.79. Did we use the right angle? 41.5 goes to 1.02. I mean, 0.679. I mean, I'm happy with this answer. I know that it's not the best answer. Cosine of 41.5, 1 over 2. Yeah, I mean, this is the answer I got. I'm perfectly happy with this answer. They got 0.679. I got 0.681. It could have been a little bit better. You can also probably use your lambda final. I mean, I wonder if you use this, you'll get a little bit closer answer. But again, I'm perfectly happy with this answer. I think it's a perfectly valid way to get here. And then the only, better way, I guess, would be 4451, right? And then 68. So, okay, so yeah, if you use 4451, 09, now you're 68.0, which is very close to 68.0, right? You'd round this up, and you get mega electron volts. So let me know if you have any questions.